A century ago, runway construction meant men with shovels, horses, and string lines. Yet they were asked to deliver math-perfect landing strips for the fastest machines on Earth. In 1919, Orville Wright warned that grassy fields would doom aviation unless something changed. Without lasers or computers, early crews achieved inch-level precision across 1,000 feet, racing to meet demands that outpaced technology itself. What was the secret behind building runways by hand, when every mistake could mean disaster? The answer begins with a surge in aviation few believed possible. By the early 1920s, aviation's promise was running into the hard limits of muddy fields and ragged grass. Airplanes grew heavier and faster almost overnight, but their landing spots barely changed. Pilots still aimed for whatever stretch of open land seemed flattest, hoping recent rain had not turned the ground to soup. Orville Wright in 1919 warned that unless aviation found a way to build and maintain proper landing places, the whole industry could stall. It was not just about comfort or convenience. Bad runways meant broken landing gear, torn fabric, and sometimes lives lost. Demand for air travel and mail delivery exploded after World War I. By the late 1920s, the United States alone counted more than 100 cities vying to become aviation hubs. But grass fields could not keep up. Each new generation of aircraft needed more. A Ford trimotor weighed over 13,000 pounds fully loaded, and even that was light compared to what was coming. The first paved runways were not a luxury, they were a necessity. In 1928, Henry Ford built a concrete runway at his Dearborn Airport, setting a new expectation. Before Ford Field, pilots braked on dirt or grass, skidding through ruts and puddles. Concrete changed everything. Suddenly, planes could land and take off in almost any weather, and airports could promise reliability, not just hope for it. But concrete was expensive, and so was the labor to lay it. Most airports still relied on grass or dirt fields, sometimes just mowed pastures marked by a windsock. These fields worked until they did not. Heavy rain, winter thaw, or a single overloaded landing could turn a flat field into a patchwork of soft spots and holes. The risk grew as aircraft size and speed increased. By the 1930s, commercial airliners and military bombers demanded runways of 2,000 feet or longer, built to handle wheels that could punch through soft ground in a heartbeat. Engineers faced a race against time. Demand for longer, flatter, stronger runways pressed in from all sides, but the tools for precision construction lagged behind. There were no laser levels, no computer models, and not even reliable bulldozers in many places. Instead, crews worked with what they had: transit levels, wooden stakes, and a relentless focus on getting every grade, every slope, every inch as close to perfect as human hands could manage. The pressure was constant. Every new aircraft model arriving on the market meant another round of calculations, another stretch of ground that had to be measured, leveled, and reinforced by hand. The need was clear. If aviation was going to move beyond the age of grass fields, it would have to invent new ways to build runways, ways that could deliver precision without the benefit of modern machinery. The next step was figuring out how to achieve that, one sightline and one stake at a time. A chief surveyor stepped onto the field before a single shovel touched the ground. In his hands were a brass-bound transit level, a battered field notebook, and a wooden stake sharpened at one end. The task was to turn uneven, unpredictable earth into a surface flat enough for a fully loaded airliner, without electronics, lasers, or even reliable power. Every inch counted. To establish a true centerline, the crew began by driving a series of hubs, thick wooden stakes, at intervals of 50 to 100 feet along the planned runway's length. The transit level, perched on its tripod, became the nerve center. Through its lens, the instrument man sighted each stake, aligning them with a distant reference point. Even a half-inch error across 1,000 feet could mean disaster for a landing aircraft. The surveyor's team worked in a well-rehearsed rhythm. One rodman held a tall leveling rod steady on a stake, while another adjusted its position, waiting for a nod from the instrument man. The chief called out readings, numbers that told the crew how much earth to cut or fill at each spot. These readings had to be precise. On WPA-era projects like Cleveland Hopkins in 1937, field logs recorded vertical tolerances as tight as 1/100th of a foot, about 1/8 of an inch, over hundreds of feet. Such accuracy was not a luxury, it was survival. Leapfrog leveling was the day's choreography. The instrument man set up the transit, took a reading, then moved ahead, with the rodmen alternating positions. For every 250 feet, the process repeated, ensuring that no error crept in as the line advanced. To check their work, crews often performed double back runs, verifying that the elevation at the starting point matched the end result. Any discrepancy, even as small as a 1/4 inch, meant restaking and remeasuring. Across the runway's width, stakes marked out the crown, the gentle arch that shed water to the sides, and the slopes that would direct runoff away from the landing surface. String lines stretched between stakes acted as both guides and warning lines. Any mound or dip rising above the string had to be cut down or filled in. For a 7,000-foot runway at LaGuardia in 1939, survey teams set stakes every 50 feet with offset markers for cross-section checks. Each stake carried a coded mark, sometimes a dab of colored paint, sometimes a pencil notation, telling earth-moving crews exactly how much material to add or remove at that spot. Wind, heat, and even the time of day threatened accuracy. Early morning or dusk offered the best conditions, as heat shimmer and air refraction could throw off readings. Rodmen learned to steady their tools against gusts, and the chief surveyor kept a close watch for signs of drift in the instrument's bubble level. If a stake settled overnight, it was pulled and reset. Every step relied on human vigilance. The crew's repeated checks and relentless attention to detail meant that by the time earth moving began, the runway's boundaries and grades existed not just on paper, but staked into the ground, accurate to within an inch over a stretch that could span half a mile. In an era before automation, this was precision achieved through discipline, teamwork, and the relentless pursuit of level ground. Rail cars loaded with cement, gravel, and steel rails snaked across the countryside, bound for airfields that often existed only as a set of stakes in a muddy field. Every ton of gravel, every barrel of cement had to arrive on schedule or risk throwing off the entire construction timeline. In the 1930s, a single missed train could mean a week's delay, as there were no overnight shipments or backup fleets waiting in reserve. At LaGuardia in 1937, city records show gravel arriving from upstate quarries, dumped in towering piles beside the future runway. Sand was dredged from riverbeds, sometimes hauled by barge to city docks, then transferred to trucks or horse-drawn wagons for the final miles. Cement shipments rolled in by rail, their schedules coordinated days in advance to match the progress of grading and formwork. Remote sites faced even greater challenges. In the Midwest, some airfields had to quarry stone on site, using dynamite and hand tools to break up local rock. Workers crushed the stone with portable crushers, feeding the results into wheelbarrows or small trucks. In places without rail access, materials moved by wagon, a process that could stretch a simple delivery into a multi-day ordeal. Municipal purchasing agents tracked every shipment, knowing that a shortfall in gravel or a late cement car could halt work across the entire site. Stockpiles grew along the runway alignment, each material staged for the precise moment it would be needed. Crews built temporary roads and laid planks across soft ground to keep wagons and trucks from sinking. Foremen counted loads by the dozen, marking chalk tallies on wooden boards nailed to the supply shed. Communication was basic, messages relayed by runner or, in some cases, by telephone lines strung up just for the job. Every delivery had to be timed to avoid bottlenecks, especially before a concrete pour when the window for placement was measured in hours, not days. The entire supply chain moved in rhythm with the construction schedule. If gravel or sand arrived too early, it risked being washed away by rain. Too late, and dozens of laborers stood idle, waiting for the next train or truck to appear on the horizon. In an era before just-in-time logistics or computerized tracking, the success of a runway depended as much on the timing of deliveries as on the skill of the crews who would soon reshape the earth. Topsoil, sometimes a foot deep, had to be stripped away before anything else could happen. Crews swung pickaxes into packed earth, shovels biting into sod that had never known a plow. Wheelbarrows lined up in rows, each one filled and dumped by hand, over and over, as the surface was lowered to reveal the firm subgrade underneath. At larger sites, steam shovels grumbled to life, their iron buckets scooping up earth in great arcs. But even these machines needed teams of men to keep them moving, oiling gears, guiding cables, clearing jams. Horses pulled slip scrapers and dump wagons, their hooves churning up clouds of dust as they hauled load after load away from the future runway. Nothing about this work was easy. Even with steam power, most of the labor came down to muscle and endurance. Removing high spots meant cutting into hillsides or knolls, sometimes moving hundreds of cubic yards of dirt just to shave a few inches off the grade. Low spots got filled in layers. Crews tipped soil from wheelbarrows, then spread it with shovels and rakes, always careful to keep the surface as even as possible. Every time a load was dumped, a foreman checked the level, calling out corrections. Too much fill, and it had to be scraped away again. Too little, and the next load had to be spread thinner. In wet weather, the work slowed to a crawl. Mud clung to boots and wagon wheels, turning every step into a struggle. In dry spells, dust coated faces and filled lungs, settling in the creases of hands that never stopped moving. Temporary plank roads were sometimes laid down to keep carts from sinking, but there was no way to avoid the grind. Some days crews advanced only a few feet at a time, fighting both the elements and the stubborn ground itself. By the end of site preparation, the landscape looked nothing like it had before. Hills were cut down, hollows filled, and the entire area shaped into a rough but recognizable runway profile. The surface was still far from finished, but the hardest part, the bulk earthwork, was done. The ground was now ready for the next stage, fine grading, where inches and fractions would matter even more than tons. A field was transformed into a runway only when every inch of earth matched the surveyor's stakes, and that demanded a different kind of precision. The rough grading left hills flattened and hollows filled, but the surface still rippled with small rises and dips invisible to the eye. Now came the work of fine grading, where fractions of an inch made the difference between a safe landing and a shattered wheel. The main tool was the Fresno scraper, a curved steel blade mounted on runners and pulled by a team of horses or sometimes an early tractor. Each pass of the Fresno cut or carried a thin layer of soil, the operator adjusting the depth by shifting a lever. Crews worked in organized lifts, shaving off high spots and feathering soil into low areas, always guided by the stakes and string lines set by the surveyors. The process was slow, repetitive, and exacting. After every few passes, a foreman walked the line with a grade rod and level, checking that the ground matched the prescribed elevation. Where the rod showed too much earth, the scraper went back to work. Where it showed a hollow, fresh soil was brought in and spread by hand. This cut and check cycle repeated across the entire width and length of the runway. At LaGuardia's 7,000-foot strip, records show that each 100-foot section could require a dozen adjustments before it passed inspection. The surface was not just flat, it was shaped with a purpose. The center line stood slightly higher than the edges, creating a crown to shed rainwater. Slopes dropped away at a steady rate, often about 2%, to prevent water from pooling and softening the ground beneath. Every adjustment was checked against the survey stakes, each marked with the exact cut or fill needed at that spot. Errors were not tolerated. If a section drifted out of tolerance, sometimes as little as a half-inch, the stakes were reset and the process began again. The work demanded patience and teamwork. Horses grew tired, men swapped out on the scrapers, and the foreman's eye never left the grade rod. It could take days to finish a single stretch, but nothing moved forward until the surface matched the plan. Only then could the crews prepare for the next step, locking the earth in place so it would hold steady under the weight of the world's newest machines. Rain was the enemy of early runway builders. Even the most carefully leveled earth could turn to mud overnight, swallowing wheels and stranding planes. Water didn't just make landings risky, it threatened the entire investment of time, labor, and material. Before a single load of gravel or concrete went down, crews attacked the problem head-on. The first task was to give water somewhere to go, and that meant digging. Laborers lined up with shovels, carving out ditches along both sides of the future runway. In the 1930s, a typical runway might have a drainage channel running its full length, sloped to carry rainwater away from the landing surface. Ditch depth varied with the site, but 2 to 3 feet was common, enough to intercept runoff before it pooled. The work was slow, muddy, and relentless. Teams advanced by the yard, sometimes in soil so wet that every scoop filled with water before it reached the pile. Where the ground stayed soggy year-round, engineers called for underground drainage. Crews laid clay tile pipes, short cylindrical sections joined end to end, buried beneath the surface at carefully calculated slopes. Each tile was set by hand, checked with a carpenter's level, and backfilled with gravel to keep the water flowing. The slope had to be just right. Too steep and water rushed past, eroding the channel, too flat and it stagnated, inviting blockages that could back up under the runway. WPA field manuals from the era prescribed a minimum slope of about 1%, 1 foot drop for every 100 feet of pipe. The surface itself was shaped with water in mind. Instead of a flat slab, the runway was built with a gentle crown, usually about 2% higher at the center than at the edges. This subtle arch, barely visible from ground level, directed rain to the ditches before it could soak in. Stakes and string lines marked out the crown, and every pass of the scraper was checked to make sure the slope held true. For a 7,000-foot strip, that meant the center line might stand more than 2 feet higher than the shoulders at either edge. Drainage was more than a technical detail. Without it, even the strongest concrete would crack and buckle as water seeped underneath, freezing and thawing with the seasons. Early failures made the lesson clear. At one Midwest airfield, a single summer storm left standing water along the runway's edge, softening the base so badly that the next landing tore a rut 2 feet deep. Repairs took weeks and cost more than the original drainage system would have. After that, no engineer argued about the value of ditches and tiles. Every detail was double-checked. Ditches had to be clear before compaction began, and tile pipes were tested by pouring buckets of water at the inlet to watch the flow. If water pooled anywhere, the crew went back with shovels and levels until it drained away. The process was repetitive, but there was no shortcut. Only when the ground stayed firm after heavy rain did the project move to the next stage. The future of the runway and the planes that would use it depended on getting drainage right, 1 shovel and 1 tile at a time. Steam-powered rollers, some weighing as much as 15 tons, lined up at the edge of the graded earth. Their boilers hissed, gears clanked, and the heavy iron drums began their slow crawl across the future runway. The goal was simple but relentless: squeeze every last pocket of air from the soil, gravel, and fill until the ground was as dense as nature would allow. Each pass of the roller pressed the surface tighter, forcing the particles to lock together. But a single trip was not enough. Crews counted the passes, sometimes 20, sometimes 30 or more over the same stretch, because anything less risked future settling that could shatter concrete or buckle asphalt under a landing plane. The compaction schedule stretched for weeks. After every few passes, the foreman would step forward with a steel probe or a heavy rod, driving it into the earth to test resistance. If the rod slipped in too easily, the roller went back to work. Only when the ground fought back, when the rod bounced or refused to sink, did the crew move forward. The process was methodical, almost ritualistic. Each section of the runway was treated in turn, with no shortcuts allowed. Edges and corners, where the steamroller's bulk could not reach, were finished by hand. Laborers swung iron tampers, heavy flat-bottomed tools, lifting and dropping them in a steady rhythm to pack the soil as tightly as the roller did in the center. It was exhausting work, demanding strength and patience in equal measure. 100 feet of edge could take hours to finish, the tampers rising and falling in a chorus of dull thuds. The difference between a well-compacted base and a hurried job showed up months or years later. On some early fields, a soft spot left by a careless crew would sag after the first hard rain, creating a depression that could snap an axle or send a landing gear through the surface. Engineers learned quickly, density was not negotiable. The heavier the aircraft grew, the more unforgiving the standards became. WPA manuals from the 1930s specified minimum densities for each layer, with field tests required before any paving could begin. If a section failed, it was ripped out and compacted again. No exceptions. Steamrollers worked slowly, sometimes advancing only a few dozen feet per hour. Rain could halt progress for days as wet soil refused to compact and risked turning to mud under the roller's weight. In dry spells, water carts sprinkled the surface to keep dust down and provide the right moisture for compaction. Balance was delicate. Too much water and the soil turned slick. Too little and it stayed loose. Crews adjusted by feel and by experience, relying on the judgment of men who had spent years reading the ground beneath their boots. By the time compaction was finished, the earth beneath the runway was transformed. What began as loose fill and raw soil was now a dense, unified mass, capable of supporting the massive loads to come. Only then could the next layer, concrete or asphalt, be considered. The patience invested in compaction paid off every time a fully loaded airliner touched down and rolled safely to a stop, its weight borne by ground that would not yield. A portable concrete mixer rattled to life near the edge of the graded earth, its drum powered by a sputtering gasoline engine. The air filled with the scent of wet cement and diesel exhaust as laborers hauled sacks of Portland cement, shovels of river sand, and buckets of gravel to the mixer's open mouth. Timing mattered. Each batch had to match the foreman's ratio exactly. Too much water and the slab would crumble under a landing gear. Too little and it would harden before it could be shaped. The lead foreman, sleeves rolled and clipboard in hand, checked every load. He watched as the mixer spun, counting revolutions and calling out when the drum was ready to tip. Crews scrambled to wheelbarrows, catching the heavy gray slurry before it could set. Forms made of rough timber lined the future runway, set to hold the concrete in place as it was poured. Laborers dumped the mix in sections, spreading it with shovels and rakes. The surface had to be even from edge to edge, so a pair of men worked a long screed board, sometimes just a straight plank, back and forth across the wet concrete, shaving off high spots and filling in hollows. The goal was a slab thick enough to support tons of rolling weight, but smooth enough that a tire would not catch or bounce. On hot days, the race was on. Concrete began to stiffen within minutes, so every hand moved fast. Trowels flashed in the sun as edges were finished, corners rounded, and the top surface worked to a fine, even sheen. The mixer never stopped. As one batch was poured, another was already spinning. The foreman kept a close eye on the clock, knowing that a delay could ruin a whole section. If a batch sat too long, it was dumped and replaced. Wasted material was better than a weak spot in the runway. Sometimes steam-powered mixers were used instead, their chuffing engines driving the drum and heating water for the mix. Regardless of the power source, every load was tested by eye and by feel. The foreman would grab a handful, squeeze, and let it fall, judging the slump and consistency before giving the nod to pour. Finishing tools were simple but essential: steel trowels, wooden floats, and heavy rollers for the final pass. As the new concrete set, workers covered it with wet burlap or straw, shielding it from drying winds and sudden rain. Curing took days, sometimes a week, before the surface could bear weight. Only then could the forms be stripped away, revealing the first finished stretch of runway, flat, strong, and ready to take whatever the future might land upon. A kettle of asphalt, heated to over 300 degrees Fahrenheit, hissed and bubbled at the edge of the runway. The clock was already ticking. As soon as the batch reached the right temperature, the crew moved fast, no second chances. 2 men dipped heavy buckets, their gloves slick with tar, and hustled them to waiting wheelbarrows. Every trip from kettle to ground was a sprint. If the asphalt cooled by even 30 or 40 degrees on the way, it would clump and resist the rakes. At the spreading line, a dozen workers stood ready, rakes and lutes in hand. The foreman's whistle cut through the noise, a single sharp blast that signaled the start. Asphalt hit the ground in thick, steaming waves. Each man had a set territory, raking the black mass into a layer barely more than 1 inch thick. The crew moved with practiced urgency, eyes on the surface and ears tuned for the next whistle. Too slow, and the asphalt would stiffen before they could smooth it. Too fast, and the layer would be uneven, risking cracks after the first hard freeze. The heat was relentless. Kneeling close to the asphalt, workers felt it radiate through their boots and up their legs. On a cool day, the surface temperature could drop below 200 degrees in under 15 minutes. In that narrow window, the entire section had to be spread, leveled, and ready for the roller. A second whistle, 2 short blasts, meant the rakes were clear and the roller was coming. The steamroller, weighing nearly 10 tons, lumbered forward at the edge of the hot mat. Its iron drum pressed the surface, squeezing out air and forcing the asphalt to seal tight against the graded earth below. Timing mattered. If the roller waited too long, the asphalt would cool and shatter under the weight. If it started too soon, the mix would squeeze out to the sides, leaving ridges and hollows. Crews learned to judge by sight and by feel, watching for the moment when the surface gave just enough underfoot. There were no second chances. Each batch from the kettle had to be handled with precision, the entire team moving as one. The foreman's whistle, the shout of a raker, the chug of the roller's engine, every sound was part of a race against cooling. In less than half an hour, the difference between a smooth, durable runway and a patchwork of failed repairs could be decided by a few lost degrees and a minute's delay. For every foot of runway, the heat dictated the pace, and the crew's urgency was written in sweat and steam. A single rope stretched the length of the new runway, pulled taut and staked at both ends. This was more than a guide. It was a promise that every landing would begin and end in a straight line. Crews knelt with buckets of whitewash and brushes, following the rope's edge as they painted the center line by hand. Chalk lines snapped across the surface, marked where distance numbers and edge stripes would go. Every letter, every arrow was measured and painted with the same care as the concrete itself. There were no machines to keep the lines straight or the spacing perfect, just a steady hand and a practiced eye. A veteran crew member, sleeves rolled and face streaked with dust, remembered the rhythm of those final days. The whistle blasts cut through the morning haze. 1 short call to start, 2 to change sides, 3 for a break. The work was relentless, but the system kept hundreds of hands moving as one. Foremen walked the length of the runway, chalkboard in hand, checking off each completed section and calling out the next task. Mistakes were fixed on the spot. If a line strayed, it was scrubbed and repainted before the paint could dry. The days stretched long, often starting before sunrise and ending after dark. Asphalt fumes clung to the air, and the heat from the surface radiated up through boots and gloves. On the hottest days, the ground itself shimmered, and workers carried extra water just to keep from collapsing. The risk was constant: steam from the rollers, burns from the asphalt kettles, and the ever-present danger of exhaustion. 10- and 12-hour shifts were common, especially as deadlines loomed. No one wanted to be the reason a runway missed its first scheduled flight. Yet even with the pressure, there was pride in the details. The last brushstroke on the center line, the final whistle signaling completion, brought a quiet satisfaction. For many, this was more than a job. It was a chance to leave something solid and lasting, a surface that would bear the weight of planes and dreams for decades to come. The runway, now marked and measured, stood ready, its lines straight, its numbers clear, built by hands that understood both the cost and the value of precision. Every time a jet touches down on century-old concrete, it's a reminder. Precision and endurance do not require modern machines, they require human resolve. As airports today face record traffic and climate pressures, the foundations laid by hand still hold. The true legacy is not just in what stands, but in what endures when technology fades. How we build now determines what survives tomorrow. Share your thoughts on this legacy.